So this workshop, is kind of a joint effort of the Obfuscation Center and the General Bay Area Crypto Day. And as a result, we wanted to have not just a continuous sequence of obfuscation papers, but also general crypto results. And so this is what this session is about. And there'll be another session like this tomorrow, too. So with that, we're going to hear about micropayments.
Thanks, Dan.
All yours, yes.
So I'm sure you guys have had enough of I/O for one day. So I'm going to give you a little break. So I'm here to talk about a recent paper on constructing decentralized anonymous micropayments. And this is joint work with Alessandro, Matt Green, Jingcheng Liu, Behan, who's in the back too, and Ian Mears.
So is that Dan?
Yes, Dan. And the paper is up on ePrint. So let's start. Everybody hates ads, right? They're invasive, they distract from content, and sometimes they even serve malware. So nobody likes ads. But websites still need some form of revenue to function. So how about instead of us getting ads, we just give the website owner some money and don't get any ads at all? So the current model is you request a website from the server, and the server sends you back the web page plus an ad. So we do away with this. And instead, when I make a request, I additionally send along some money and get back a web page without any ads. The problem with this is that for most credit card payment systems today, for example, you're paying a large transaction fee when the value of the transaction itself is probably quite small. So for example, like ad impressions are less than 1 cent, but transaction fees for credit card networks are 20 cents. So this is not really practical from like any point of view, and I don't think any website owner is going to adopt this. So we can't use common payment systems. And one approach to solve this problem is via micropayments. And micropayments have a rich history in crypto. For the past 20 years, there's been a lot of work on constructing different kinds of micropayments, and even some deployed systems from like esteemed cryptographers like Sylvia McCarley and Ron Rivest. So you could say this problem is solved in some sense, but not quite. Despite all this effort, micropayments haven't seen any widespread adoption. Potential reason is that nobody actually cares for what micropayments can give you, but I don't think this is really true because you have models like app stores, iTunes, and even like the Brave browser, which gives you this payment instead of ad functionality. And they all use techniques which stem essentially from micropayment literature on micropayments. So a better reason would be that all these schemes that we see here, they require some central mediator to act as an intermediary between the content owner and the person who's buying the content. And this is an issue because it requires creating complex financial relations between the different parties, meeting regulations, and so on. So maybe we should look at some decentralized systems. And before we go on, I just want to draw your attention to the first kind of micropayment technique. And this is like a probabilistic payment scheme where instead of paying you 1 cent for every transaction that I make, I pay you $1 with probability 1 over 100. So in expectation, you get the correct value, like 1 cent per transaction, but your transaction fee is amortized over the 100 transactions. So just some terminology I'm introducing. So if Alice wins the coin flip, and so Bob doesn't get $1, we'll call it null payments. But if Bob wins and gets $1, we call it a macro payment. OK, cool. So let's go back to considering decentralized currencies. We've had like eCash in crypto for a long time, but it's only really taken off when a decentralized technology came about, and that was Bitcoin. So for the past few years, Bitcoin has seen rapid adoption among people across the world. And part of the reason for this is that to pay someone, you don't need to create a complex business relationship with them. You don't have to talk to banks and regulators and so on. All you do is, if Alice wants to pay Bob, she just signs a message saying from A to B and so amount. And that just goes on the ledger. And the parties maintaining the ledger just eventually approve it, and Bob gets this much money in his account. So can we use Bitcoin to construct micropayments? There's a few problems with this. One is that even for Bitcoin, transaction fees are relatively high. For instance, I was looking yesterday, and they're I think the same price as credit card transaction fees. And they're only going to get higher as Bitcoin scales and gets more users and tries to scale. The second problem is transactions on Bitcoin take a long time to confirm. Each block takes roughly 10 minutes to appear on the ledger. And I think the recommended practice now is to wait for 6 blocks before confirming a transaction and giving the item that the buyer wanted. And this is particularly bad for micropayment applications because what you're buying is of really small value, so you want to get it pretty quickly. For instance, you're browsing the web, you don't want to wait 10 minutes to get back the web page from the browser. And the third problem is that Bitcoin has no anonymity whatsoever. The sender, receiver, and the amount of every transaction are all public on the ledger. And there's been lots of interest, both from academia as well as commercial entities, trying to de-anonymize the transaction graph and find out, infer some information about transactions on the network. And the consequences of this are that you don't have any fungibility. Now, what's fungibility? It has nothing to do with mushrooms, but rather it just means that no matter if I have 2 coins of equal value, no matter the history, they'll be treated equally. So if it comes from Trump or Hillary, it doesn't matter. It's always going to be treated equally. And no merchant can refuse to take it if it's from Trump, for instance. So you don't have any fungibility, but you also don't have any privacy for users. And this is especially bad for micropayment applications because, for instance, if you have a micropayment for web browsing, you don't want your browser history to be visible to everybody in the entire world, right? OK, so there's been some sequence of works over the past few years trying to resolve this. And to solve the first 2 problems, there was a paper by Pass and Shalat at last year's CCS, where they constructed probabilistic payments for Bitcoin. And just to recap, here, when Alice wants to pay Bob, instead of paying him $1 each time, she just pays him 1 cent with probability 1 over 100 for a transaction. So how does it solve problems? It amortizes the transaction fee, so you're not paying the entire transaction fee for every micropayment. And also gives you quick confirmation because your null payments, when Bob doesn't win, they don't go on the ledger. Only the macro payments go on the ledger. So you don't have this issue of having to wait for the transaction to be confirmed. OK, so this solves the first 2 problems, but we're still left with anonymity. And a separate work called Zero Cash at Oakland a couple of years ago solves the first problem, the third problem, sorry. It creates an anonymous, decentralized Bitcoin-like currency, and which hides and every transaction, the sender, receiver, and amount of every transaction are completely hidden from anybody looking at the ledger. But it doesn't solve the first 2 issues. So you still have slow transaction confirmation and high transaction fees. So ideally, what we'd like to do is get the best of both worlds, combining the advantages of the Pass and Shalat scheme and the anonymity of Zero Cash. So we want micropayments that are decentralized to get easy deployment, and anonymous for fungibility and privacy and so on, and offline, which just means that null payments don't go on the transaction ledger. And this gives us fast responses. And what we get is we define a cryptographic primitive that achieves all these properties. We have an ideal functionality. The ideal functionality part is important because we'll have some intra-epoch issues, which I'll explain later. And we get a construction under standard cryptographic assumptions like NISX and one-time signatures. And to do this, we use 2 main techniques. One is game theory, which gives us a good characterization of double spending, which, as we will see, isn't preventable in our setting of when we're working in the offline setting where null payments don't go on the ledger. And we use this cool technique called translucent cryptography, which gives us a probabilistic message transfer. So I can give Alice a message, or give Bob a message, and he'll only be able to decrypt it with some probability that we agreed on before. And this term translucent crypto comes from a paper like almost 20 years ago by Bellari and Rivest, where they used it for key escrow. So the government can decrypt your message with probability, with some small probability, but not always. So your message is translucent. And yeah, so that time it was, I guess, a negative use, but now we're using it to help the people, I guess. So let's go back to our building blocks. What Parse and Shallot do is essentially they take Bitcoin and add some kind of coin flipping protocol. So when Alice wants to pay Bob in a micropayment, what she does is ascribes some value in a Bitcoin transaction. They engage in a coin flipping protocol. If Alice wins, that means it's a null payment. She can reuse the escrow for future payments. But if Bob wins, he gets the value, and a transaction appears on the ledger, transferring the escrow's value to his account. So that's Parse and Shallot, and it's pretty simple. What Zero Cash does is takes Bitcoin and adds anonymity via zero-knowledge proofs. So in Zero Cash, money is stored in coins, and each coin is associated with a commitment, which appears on the ledger when the coin is created, and a serial number, which appears on the ledger when the coin is spent. So to pay Bob, what Alice does is derives a serial number for her coin. Let's say she owns a coin C1 with commitment CM1. She derives a serial number using her coin as well as her secret key, creates a new coin for Bob using his public key. Let's say this coin is commitment CM3. Creates a proof that she did all of these steps correctly, and appends the transaction to the ledger. This transaction consists of the old serial number, the new coin commitment, as well as the proof. So the cool part is that there's no way to link a coin's commitment with its serial number. Even though they might appear in the ledger, unless you have the secret key, there's no way to link the two. So essentially, the ledger always looks like a string of random, a big table of random things. OK. So one naive attempt would be to try to combine Parse and Shallot, then Zero Cash, and let's see what happens, what goes wrong in that scenario. So you proceed as before, but now Alice just ascribes her money in a Zero Cash transaction that goes on the ledger. And Alice and Bob, as before, go participate in a coin flipping protocol. Now, if Alice wins, again, she can reuse the escrow. And if Bob wins, he gets V. Why doesn't this work? Well, we have two major issues. Alice doesn't actually have much privacy, and she can double spend. So let's dive into some more detail. The problem is that for every transaction, Bob gets to look at the escrow and learns the serial number of the escrowed coin. So this leads to two kinds of attacks. In the first one, he can track Alice as she makes micropayments with him. So say she transacts once with him, it's a null payment, and Bob gets to see the serial number. Then somebody else comes along, they transact, it's a different serial number. And then Alice comes back, and again she transacts, but now Bob can see that the first and last serial numbers are the same. So he knows that Alice must have transacted with him in the past. Similarly, he can also, and perhaps this is like even a worse attack, he can track Alice when she spends not only with him, but also with other merchants. So let's say she spends it with Bob, and he sees some serial number. And then she tries to transact with Carol, and Carol gets the transaction, which she posts on the ledger. So this transaction contains the serial number, and Bob can see, oh, Alice must have spent the coin that she tried to use with me.
Why does she have to use the same serial number? Why can't she just roll the coin over and use that the next time?
So if she transfers her coin to a new serial number, she has to essentially, that has to go on the ledger, right? So it'll be, she'll have to pay transaction fees for that. And it'll be slow. So yeah, she can't just refresh the coin every time, because that would be slow and cost transaction fees. Yeah, so essentially we have no privacy in this setting. So our solution is to make the serial number translucent. What we do is, instead of putting the escrow transaction on the ledger, Alice commits to it and sends over the commitment to Bob. And then they try to open it probabilistically. So when a null payment happens, Alice can spend the coin again, but Bob learns absolutely nothing about the serial number. If a micropayment happens, then he learns as what he did before and can post a transaction to the ledger. Our primary tool for this probabilistic opening is a fractional message transfer, FMT scheme, which gives us two properties. Fractional hiding, which means that Bob learns the message only with probability P, and otherwise he learns nothing. The ciphertext looks like encryption of a random string. And fractional binding, which means that Alice can't somehow malleate the ciphertext to lower the probability that Bob can open the ciphertext. So Alice wants fractional hiding, and Bob wants fractional binding, and so FMT is essentially the perfect tool for our scenario. And we construct FMT schemes using standard crypto assumptions like DDH and random oracle, and it's a two-message scheme. I don't know if you can go lower than that. It's not oblivious transfer-based. I mean, it's a similar kind of, I guess, tool, but it's not OT-based. I don't think so. OK, so we solved this linkability issue. But we still haven't, but how can Alice double spend? So what she can do is, first attack she can participate in is use the same coin with multiple merchants at the same time. So say she's interacting with these 4 people in a probabilistic payment, and 2 of them get a transaction. Say Carol gets a transaction and Bob gets a transaction. If Carol posts a transaction to the ledger first, and then Bob tries to go, he won't get any money at all because the coin has already been spent. So Alice has gained free utility, and Bob is like robbed of his money. Similarly, Alice can again, whenever Bob gets a payment, she can front run. That should be a guy there. She can front run Bob to the ledger and then spend the coin to herself. So say she gets the transaction, but Alice races, I guess it's Carol now, to the ledger, and when Carol tries to put a transaction, it can't go on because the coin has already been spent. And this is in some sense endemic to our setting because null payments don't go on the ledger. And we want this fast response time, so we can't wait for the ledger to confirm a transaction, like whether or not the coin has been spent before the merchant responds. The merchant has to respond immediately, and so we can't prevent this kind of attack. So at least cryptographically. So we resort to rationality, and I'll discuss that later. So our solution is to have Alice, before she makes a micropayment, to always deposit some value in a deposit coin. For the moment, we assume it's like the value of the deposit is like infinity. So if a deposit is revoked, she loses all possible utility from double spending. But later, I'll explain how we can get a good bound on the deposit value. So she creates a probabilistic payment. And now, instead of just committing to the transaction, she also commits to a secret share of the deposit serial number. And she sends over the commitment as well as the proof that she did all this stuff correctly, the deposit is valid, so on. And they engage in the probabilistic opening as before. If Bob wins and it's a micropayment, then he posts the transaction as well as the secret share on the ledger. And why does this work? Well, the idea is that if it's a null payment, Bob learns nothing, so he doesn't get a secret share. But say they transact again, and Bob gets a macro payment this time. And so he posts the transaction plus a secret share on the ledger. And say Alice tries to use the same coin again, and it's a macro payment again. Then what happens is that Bob gets a secret share. He can combine it with the secret share that's already on the ledger and recover the serial number and put that on the ledger, just revoking the deposit. So this would result in Alice getting like negative infinity utility. So she would lose all money that she gained from double spending. OK, so far, we've used probabilistic opening and deposits to prevent linkability and prevent double spending. But are we done? And the answer is not quite. There's a couple of issues in terms of usability of our system. So far, the deposits are pretty large, and we would want them to be withdrawable from the system. Like if Alice puts in like infinite amount of money, she would eventually like to take it out. But this creates another attack in which she front runs the revocation to the ledger and gets back her deposit before it can be revoked. And similar attack happens. Okay. So far we've considered malicious Alice, but what if Bob is malicious and he refuses to answer and post the transaction to the ledger in case he receives a macro payment? So he gets the transaction and he keeps it with himself. If Alice had to spend the coin again, then a secret share will go on the ledger, and then Bob can recover her serial number and put it on the ledger, thus revoking her deposit. So even though Alice wasn't really being dishonest, she now has minus infinity utility. So we want Alice to be able to refresh the ticket again. But this leads to the same attack as above, in that she can withdraw her ticket before Bob can spend it. Like an honest Bob can spend it. And the key observation here is that we have different coins that serve different purposes in our system, but we're not treating them differently. So we have these deposits that are withdrawable, just like normal coins are withdrawable. And similarly, tickets can be withdrawn, just like normal coins can be withdrawn. So we solve this by introducing different types of coins. We have the standard, we adopt the terminology from Zcash, where they call coins notes. So standard notes allow you to do deterministic, slow transactions. So you can go from a standard note back to itself. But they also allow you to create deposits and tickets. Deposit notes are used to back tickets in micropayment transactions. But you can withdraw a deposit to a standard note with a delay. And this delay is what prevents front running, because if you try to withdraw it, then it'll take some time, and in the meanwhile, the deposit will be revoked. Okay? Tickets are used for probabilistic payments, and they take you from a ticket, and these payments take you from a ticket to a standard note. And you can again refresh them, but with a delay. And these delays prevent front running, because if you try to withdraw your deposit or ticket before revocation or redemption, I guess, goes on the ledger, then you'll fail because it'll take some time. And in the meanwhile, the honest person will have revoked or gotten the ticket, revoked the deposit or gotten the ticket. Okay. So far, I think our system is by and large secure, but we still have this usability problem that our construction is secure and usable if the deposits are infinite. But if we have a system where people are required to invest a huge amount of money before they can even participate, nobody's going to use the system. So we show that it's possible to bound the size of the deposit via some economic analysis. And the key question here is to decide what is a double spend. So say Alice is spending with two merchants in parallel, and she has initially two null payments. And yeah, she's spending with the same ticket. But these really aren't double spends, because from the point of view of the merchants, it's completely indistinguishable from an honest customer using different tickets for the payments, because they don't know anything about the underlying ticket. Okay, so those aren't double spends. But let's say now Alice gets a macro payment, which propagates across the network after some delay. In the meanwhile, however, she spent with the second merchant, and these two new payments are actually double spends. And this is the additional utility that she can get. So what we see is that the additional utility that she can gain from double spending is only the amount that she can get from the first time a double spend occurs until the merchant detects the transactions from other merchants propagating to the network. So it's not infinity, but whatever utility she can gain in this period of time. So we'd like to bound this. And how do we do this? Well, the key idea is that the additional utility per merchant is just is bounded. Okay, well, it stems from the fact that there's this inherent network delay in the Bitcoin network, where merchants only learn of other transactions as they propagate through the network, which usually I think is maybe less than 10 seconds, but that's enough time for a micropayment situation where you might browse like 1,000 web pages within 10 seconds. And the second source of utility is the number of payments that a merchant can accept during this time delay. So if you can bound these two quantities, then we would be able to bound Alice's utility from double spending. The question is, are these bounds necessary? And we show that this is the case. Essentially, we get a tight bound on the value of the additional utility. So if the network delay is unbounded, then a merchant will never learn of double spending that Alice has done with other merchants. So she can continue double spending with him with different tickets forever, essentially. So that way her utility just keeps growing and growing and growing. And this is potentially, it's not a theoretical situation. There's been work on so-called eclipse attacks on the Bitcoin network, where you just change a merchant's view of the network. Yeah, so if a merchant never learns of double spending, then Alice can get as much money as she wants from him. Similarly, if the payment rate is unbounded, where the payment rate is the number of payments that the merchant accepts within a particular time period of this network delay, then Alice can spend an unbounded number of times within that time slot, because the merchant will just keep accepting payments no matter what happens. Okay, so this is essentially the idea that, say, the person at the top has unbounded network delay, then Alice can keep spending with him. Okay, so this means that we need to bound these two quantities for an honest merchant. For every merchant, a merchant needs to set these two quantities, but this is just per merchant. We would also need to bound the number of merchants in a network. And this is a slightly tricky quantity to determine. So what we do is have the deposit be bound to some certain number of merchants. When you create the deposit, you say, oh, I can transact with this merchant. And then the value of the deposit is only determined by the payment rates set by those merchants. So what we get is a theorem which determines exactly what additional utility Alice can gain from double spending within one epoch. And to enforce these bounds, we have to go back and modify a construction. And we achieve this, but it's really technical and detailed, so I'm not going to go into it here. Okay. So in conclusion, we construct decentralized anonymous micropayments using some cool tools from crypto as well as game theory. But some broader takeaways are that our game theory analysis isn't just applicable to our situation, but also, for instance, to the Pastulat paper, where in an updated version they said that, oh, you need deposits, but they didn't quite specify the value of the deposits. So I think our analysis applies to their scenario as well. And also, they mentioned probabilistic smart contracts, and I think if you need a good understanding of how people can cheat to be able to write correct smart contracts which function as intended. Yeah, so our game theory analysis is broadly applicable, but also while constructing our system, we discovered some pain points in the zero cash interface, which resulted in us creating a more general, so somewhat programmable interface. And we'd like to see how, like, what new applications come from this extra ability to program zero cash. And we're already working on looking at some applications. Yeah, so that's all I have. Thanks. And the paper is on ePrint.
So is this implemented, used?
Not quite implemented, but it's possible, I think, to implement it. It wouldn't be with standard crypto assumptions, probably snarks. But I think it's somewhat reasonable. The main bottleneck would be that proof that you give the deposit is valid. You might have to generate that online, so that might cause some problems. Yeah.
Go back to slide 23.
Oh. Okay, let me just see if this works.
It was the issue of double payments on a non
21?
21.
Okay.
Yeah. Okay, there's two no pays.
Yeah.
You say it's not double spent, but Alice is seeing the websites, and this, if she does this right, this does not go into her 1 in 100 chance of paying. So right So
Well, the idea is that you can't.
probabilistically, she hasn't, but it has double paid.
Yeah, I mean, it's a double spend, but it's not detectable in any meaningful sense. So it's like if you have like a global view of the system, then you can see, oh, these two are double spends. But it's not possible for merchant 1 and merchant 2 to detect that it's a double spend.
So if she changes her code, I mean, doesn't it seem like she can now get away with more by doing this? Can't she see more websites before she, instead of going 100 before she pays, she might go 200 websites before she pays?
Sure, but in some sense that's indistinguishable from an honest customer using 2 different tickets to look at the websites. And she gets caught cheating when it becomes a macro payment, right? And then your deposit revokes all the extra utility that you gain from doing this. Okay. Anyway, yeah.
So get this 2-round lower bound that you mentioned.
Yeah.
Wouldn't you be able to reduce it to some other primitive round? Not just a little structure, but synchronous transmission.
We need it for, like, I think, some more. We use it in a different manner because what we do is our system, you generate a public key and secret key, and then say Alice encrypts her transaction under the public key, and then Bob decrypts it, tries to decrypt it. And at the end, he has to send back some proof that whether or not he was able to decrypt it. So these public keys that Bob generates have to be, in some sense, one time. Because if Bob uses the same public key across multiple transactions, then Alice can realize, oh, let me just encrypt it with this randomness, and he won't be able to decrypt it. So I think that's where I think maybe the 2-round lower bound comes from.
Yeah. He's giving you a proof method.
I see. Okay.
Yeah, that would be.
We can try to see what it implies as a primitive.
Mm-hmm.
I think in the proof security, having rounds is a pain. So having fewer rounds would be very welcome. We're not sure how to reduce it or whether there are any lower bounds to that prevent from getting, say, non-interactive fractional message transfer.
Yeah, not arguing for 2 rounds are good.
Great.
Okay.
Cool. Any other questions? All right,
Okay.
thanks.
Thank you, everybody.